In this video, we talk about parallel transport and covariant derivative. Imagine you are driving along the Earth's equator at a constant speed. An observer restricted to the surface of the Earth perceives only the component of the acceleration tangential to the surface. For an observer in space, the velocity is not a constant. So suppose gamma is a curve on the surface, yes, V be the tangent vector field along gamma. To an observer moving along the curve gamma, the rate of change of V is just the tangential component of rate of change of the vector V. If n is the unit normal to the surface, the component of the V dot rate of change of the velocity perpendicular to the surface is given by the projection along the standard unit normal. So the tangential component is given by subtracting the component along the standard unit normal. So rate of change of V minus the projection of the rate of change of V along the standard unit normal gives the tangential component of rate of change of V along the curve gamma. So this quantity for equation 47 is known as the covariant derivative of V along gamma. It's the projection of the V dot onto the tangent plane at a point gamma of t. So there are propositions to prove a tangent vector field V parallel along gamma along a curve gamma on the surface S if and only if the covariant derivative of V is 0. That means the V dot has only component along the standard unit normal. It does not have any other component along the curve gamma. Then we call this vector field V is parallel to the curve gamma. We have another proposition here. Let gamma is be a surface patch with first and second fundamental forms. Then the second derivative of the surface patch with respect to the parameters is expressed with the coefficients known as Christoffel symbols. These Christoffel symbols depend, one can show that these Christoffel symbols only depends on the first fundamental form, that is E, F and G. So this is the proposition. We have one more. We have the proposition to prove here is that we have a curve gamma of t be a curve on the surface patch, and let the vector field, the tangent vector field along gamma is given in terms of sigma u and sigma v, the coefficient. These are the smooth functions of t. Then this vector field is parallel along gamma if and only if these coefficients, these equations are satisfied. So one can prove this result, equation 51 and 52. What does it mean? That we have a fixed tangent vector. So if gamma is a curve on the surface, yes, V naught be a tangent vector at the point gamma t. So we have only one tangent vector which is parallel to gamma, curve gamma, parallel along gamma. So a map which takes a vector, tangent vector to at point P to the tangent vector Q, such that the covariant derivative remains 0 all along the curve. It goes from V0 to V1. Then we call this map as parallel transport. For all along this maps, this is the map which takes from the vector, tangent vector to another tangent vector at point P and Q, and these vectors are parallel to the curve gamma. So this map is called a parallel transport from point P to Q. That's all. Thank you.